Now let's look at something called the squeeze theorem, which can be a useful tool for helping us evaluate limits of certain types. Okay, so let's look at the squeeze theorem. All right, so the squeeze theorem says that if f of x is greater than or equal to some other function g of x and is also less than or equal to some function h of x near, meaning from both sides, near some x value we'll call a. So if f of x basically is between the two functions near this x value of a and the limit as x approaches a of g of x, so whenever we get close to a for the g function, if that equals the limit as we get close to a of the h function, let's call that limit L. So if the limit of the two outside functions that sort of squeeze the f function, if the limits of those are equal, and we call that L, then we can conclude that the limit as x approaches a of f of x has to also equal L. All right? And you can probably sort of picture this in your head. So let's draw our function f of x. Let's say our function f of x is, something like this, whatever. And then our function g of x is smaller than f of x. Okay. And then h of x is bigger than f of x. And then right here, this is the x value a. So you can see f is between g and h. But let's say that the limit as x approaches a of g of x is this value here, this y value, and the limit as x approaches a of h of x is also that, then the limit as x approaches a of the f function should also be the same value, L. And if you want to locate the value L, it would be the y value for this particular point. Now, this is not a one-size-fits-all diagram. It's just a quick illustration of if one function is between two other functions near this x value, and the limit of the upper function equals the limit of the lower function, then the limit of the function between should be the same as well. So let's see a couple examples of applying the squeeze theorem. So we'll start with a basic example here. So let's say we want to, we have something like this. Let's say if this function f of x is greater than or equal to 2x minus 1 and is less than or equal to, let's see, x squared minus 4 for x values greater than 0. So if f of x is between those two functions for every x greater than 0, determine the limit as x approaches 3 of f of x, okay? So I just made up this problem so we could illustrate the squeeze theorem. So don't worry about where these numbers or functions came from. I made those up. So what we see here is that so when x is near 3, we know, so whenever x is close to 3, we know that x is greater than 0. So it's true that we know that near 3, we know that 2x minus 1 is less than or equal to f of x is less than or equal to x squared minus 4. By the squeeze theorem, which I'll abbreviate as ST, the limit, well, I apologize, let me back up here a moment. So note that the limit as x approaches 3 of the lower function, 2x minus 1, well, you can evaluate that by direct substitution, is 5. And that is the same thing as the limit as x approaches 3 of the upper function, x squared minus 4, right? Direct substitution again. You can see that both of the outer functions approach 5 as x approaches 3. Now we can say, by the squeeze theorem, the limit as x approaches 3 of f of x is also 5, because the limit of the outer functions is 5 near 3. So by the squeeze theorem, the limit of the middle function has to also be 5. So that's a pretty straightforward introduction to applying the squeeze theorem. Let's see another example. Maybe that's not so obvious. Let's determine the limit as x approaches 0 of x to the 6th times the cosine of 3 over x. So this is kind of a weird one. Now, if you want to try direct substitution in this case, you'll have a problem because you'd be dividing by 0 in the argument of the cosine function, which we need to avoid. So we need to search for something else. Now, algebraically, I'm not really thinking of any way we could manipulate this so that dividing by x goes away and allows us to evaluate the limit. But the cosine function and the sine function, both of them, have this interesting property that you should be familiar with sine and cosine graphs. If you take the cosine of anything, it's always between -1 and +1, okay? So in this case, the cosine of 3 over x is between -1 and +1 for all values of x. Now that's almost true. X can't be 0 because we can't divide by 0, so we know that this is true if x does not equal 0. But it is true if x is near 0, okay, if it's close. So that's a key there. So if it's close, it's true. So if that's true, multiplying all three sides, if we multiply all three sides here by x to the 6th, so I'll multiply the left side by x to the 6th, I'll multiply the middle by x to the 6th, and I'll multiply the right by x to the 6th. Notice that x to the 6th, no matter what x is, x can't be 0. If x is negative, x to the 6th is positive. If x is positive, x to the 6th is positive. This is another key. So I'm multiplying by something positive. So my inequalities will not switch to face the other direction. So keep that in mind. You have to be careful when you multiply an inequality by an expression. All right, so if I multiply everything by x to the 6th, I get negative x to the 6th is less than or equal to x to the 6th times the cosine of 3 over x is less than or equal to positive x to the 6th. So what we've just done, just to let you know, is we've taken the original function here and we've squeezed it between these two functions. And this is true if x does not equal 0. In fact, I'm going to erase the part where x does not equal 0, and I'm going to emphasize what we really need if x is near 0. That's got to be true, right? If x is near 0, then this is true. Now, we're going to try, we're building all the structure for the squeeze theorem. So note that the limit, now I want the limit as x goes to 0. So I'm going to analyze the lower and the upper function here as x approaches 0. So the limit as x approaches 0 of negative x to the 6th is 0. And that is also true when you approach 0 of the x to the 6th function. So when I take the limit of my two outer functions, I get 0. So by the squeeze theorem, the limit as x approaches 0 of my middle function, x to the 6th times the cosine of 3 over x, has to also equal 0. So the key here is the fact that the sine or the cosine of an argument is always between -1 and 1. That sort of builds your three-sided inequality that you might be able to use for the squeeze theorem. The next thing that has to happen is the limit of the lower and upper functions that you construct have to be the same to get the middle function to have the same limit as well.